Hey everybody, and welcome back to Unison for All. I'm joined here by Heather Miller and Paul Chiusano. I'm deeply honored to introduce Dr. Heather Miller, who is an assistant professor in the Institute of Software Research at Carnegie Mellon University. She was the co-founder and executive director of the Scala Center, where she was also a research scientist. She was also an assistant clinical professor in the College of Computer and Information Science at Northeastern University. And I think it's no overstatement to say that Heather is one of the world's foremost researchers in compositional distributed systems. And she, along with Paul, is going to tell us about collaborative data structures. And Paul Chiusano is the co-founder and CEO of Unison Computing. And they're going to tell us about collaborative data structure and giving an implementation of such a thing in Unison. Take it away.
Yeah, thanks, Renar. That was like very undeserved intro. Thank you. Yeah, so this is a talk that Paul approached me and was like, hey, do you want to give a talk at Unison for All? And I'm like, yeah, sure, but let's do something together. And I completely confused Paul, I guess, and it wasn't until like 2 weeks ago or something that you realized that I had suggested that we do it like together at the same time. So I stressed out poor Paul here, everybody, just in case you were wondering. But anyway, so the way that this talk kind of came together was that Paul and I just sat down and kind of were brainstorming how do you represent some of these things that I'm going to talk about shortly in Unison, because the prototypes that we built in my research group at CMU is in TypeScript, and it's all very object-oriented, and there's lots of inheritance and stuff like that going on all over the place. And so it's like, okay, we have to like functionalify this, and then we have to try to use Unison's cool features to make it distributed. And so that was kind of like the task that we sat down to do. And I think that most of this talk is going to be kind of like what we have discovered, but in this like little exercise that I think we both did. Is that accurate, Paul?
Yeah, no, I think that's great. So yeah, and it was really fun collaborating on this.
And stressful.
And yeah, stressful because it was more because of the time crunch.
Yeah, well, I'm so sorry to freak you out, dude.
But yeah, I'll let you take it away, and I will just kind of advance the slides for you. So
sounds good. So on that note, it's just kind of a little heads up that the work that I'm going to be talking about when I start talking about these like things that I'm referring to as collaborative data structures, or collabs, we call them as well. This is actually Matthew Wiedner's PhD work. So he's a PhD student at CMU that I work with. So there's obviously more to all of this stuff, and I've included at least one paper link. I'll post the slides in the chat when this is over, so you can poke around if you're interested. But this is Matthew, and if you think this stuff is cool, you should take note of this guy because he's pretty neat, and he's going to keep doing this stuff going forward. So follow his work is what I suggest. So the way that this is structured, basically there's three parts. I'm going to start with a conceptual overview of what the heck I'm talking about. If you guessed CRDTs, that's mostly right. And then we're going to introduce kind of the pieces of the implementation that we kind of sketched out. And then Paul's going to introduce that, and then he and I are going to talk about this example that we worked out together. So that's how this is going to unfold. Yeah, so all right, I'm gonna hold on, just get on my soapbox for a second, everybody. Soapbox, on the soapbox. Okay. I have this rant that I'm always giving all the time that basically everybody has to deal with distribution in some way. Like no matter what, you write a program, you get a job, you do something with computers nowadays. If you're a programmer, you're typically having to deal with distribution and in some way, and you don't, and we all kind of pretend that this distribution doesn't exist, or at least, we don't like broadly talk about it. So what do I mean concretely? Well, I mean, I would argue that if you work with RESTful APIs, you're doing distributed programming in some way. If you are working at a company that has a bunch of microservices and you're making like requests, over a RESTful API or a gRPC or something like that, to different services in your company, that's distributed programming. And one issue that I have, I feel like I'm this person standing in like a very crowded room, like yelling, and nobody can hear me, with this sort of observation. It's like when we think about distributed systems and what gets taught in universities and whatnot, we are like led to believe that the way that you reason about distributed systems is to really just focus on different processes on different machines. And then maybe you use message passing, maybe you use RPC, but that's how you think. That's your modality for making things like interact and operate in a distributed system. And I feel like I'm screaming and nobody can hear me because I think that's crazy. Like, I don't think everybody should have to think in those terms, especially if you have to deal with distributed stuff these days, right? Yeah, I mean, sure, somebody should think of that level. Like if you are working on Zookeeper or something, if you're maintaining Zookeeper, then yes, you should know all kinds of things about consensus and, working at a very low level. But I really don't believe, I fundamentally do not believe that everybody should be forced to reason about things like this. I think that we're slowing ourselves down as programmers and we're just doing all kinds of extra, like spinning our wheels and thinking about things that I don't think we should have to think about. Basically don't, Paul, don't do it yet. So the work that I'm actually going to need you to chime in here in a second to tell me if I've characterized you incorrectly. But the work that I've been doing in my research group with my PhD students over the years has kind of been sort of focused on this notion that I don't think that people should have to use these tools. I think that we're wasting our time by having to use these tools. And we have a bunch of projects that try to make this better in various ways. And one of them is going to be the topic of this talk. But I suspect that, this notion that I just ranted about is probably also one that Paul, Renard, and Aria also share. I don't know if I'm making that up, but Paul's like,
oh, yes, definitely. Sorry, I was muted, but yeah, definitely. Just generally simplifying how we build stuff like this. I
mean, this is kind of, motivation that set you guys out to build Unison-ish. I mean, that and other things, right? But it's unnecessarily difficult is sort of is the prime observation here. So anyway, the point here is that I think that I personally believe, and I think Paul and friends believe that we should be able to program at the level that we're thinking at, and that's what we're trying to do. So the next thought. Okay, so CRDTs don't exist, everybody. Pretend that they're not real, right? So if I tasked you with building some kind of collaborative app, where would you start? Does anybody have some suggestions? Like how would you start to do this? Like, let's say you want to build a collaborative Kanban app board or a collaborative Minesweeper or something like that. If we go to the next slide, here's an example that Matthew made. It was a collaborative recipe book. I think, Stage, I was in the wrong chat link. Server client, okay. Sure, HTTP REST API. Jakub says he's a UI programmer. But then ends up dealing with a distributed data, which is totally true. I love that people think that front end development and things like that, that's just like so silly and simple, and you're just making UIs. No, you're making a whole bunch of requests to like get a bunch of distributed data and integrate it into one place. And we just don't. I don't know why we don't acknowledge that loudly. Mitchell, okay, I'm going to read this out loud because I find it hilarious. Mitchell Rosen said, I would write something underspecified, ad hoc, and then shortly before collapsing under the complexity of my own creation, I would quit and find a new job. Very good. Yes, that's kind of how to do these things, right? So Matthew uses this example, and I like this example. recipe app. And so, let's say that we have this recipe app and that we'd like to make it collaborative. So there's like, the way that this app works is there's a bunch of recipes on the left, and you click them, and then you can see the ingredients, and you can futz with them. But this is how, and you can scale it up or down or whatever. He found this on CodePen, and then he took it and he added some features to it. But it's basically a little TypeScript app, a little JavaScript app that runs in the user's browser. And it's the kind of thing that you could probably just make over the course of a weekend or something, or an afternoon, right? Like, it's not like if I'm like, hey guys, do this, like build this thing. Like, I think most people in this talk would be like, okay, I know how to get started. Obviously, you choose one of 18,000 different JavaScript frameworks, and once you've chosen the perfect out of 18,000 JavaScript frameworks, you just put the pieces together, right? And then to make it collaborative, okay, well, that obviously that's more difficult. You probably would start being like, okay, this has to be a full stack app, right? We have to have a back end for this. We can't just have it live only in the user browser. We have to run some servers. We're going to have to set up some synchronization protocols because, this is supposed to be collaborating on an app, or on the data in a recipe app. We're going to have to deal with user account security. And we're going to have to obtain money to run these servers, right? So like suddenly things obviously get more complex. And then, let's not even talk about the situation where like people actually start using it, right? And then, it's on Hacker News for an afternoon, and what happens? It explodes promptly. So yeah, it's not super straightforward how, and it's a lot of work. So regardless, it's like not immediately obvious how you would make the collaboration happen. You would synchronize somehow. But then, it just kind of explodes from this like simple thing that was data sitting in your browser that you were like manipulating to this ginormous thing that is expensive, and we don't even know if it's going to work. And it definitely is probably just going to collapse. Like Mitchell said, right? Like it would just collapse under its own complexity, right? So, at this point, Matthew makes this quip. He's like, well, at this point, you're probably thinking about quitting your job and starting a startup to like make this app collaborative, basically. And I mean, that's sort of like an example of the Herculean effort that you have to invest in making things collaborative. Like think about how many startups are out there right now that basically offer some product, but collaborative-ified, right? Like, because it's so hard. That's why it's really hard. So anyway, that's where, this, oops, next slide, Paul. So we have this nice little, like featured comparison thing, right? So like the TLDR of this is that, well, if I'm going to have like a single user static app that like sits on my web server or something, clearly the deploy is really easy. I can just, it should be easy to build because, you should just grab your JavaScript framework and put it together. Privacy is satisfied because all of your data is on in your browser. Like nobody has access to that. Longevity in terms of you can just keep it running. Obviously offline mode. No collaboration, but hey, it's forkable. You can just put it online and someone else can do something with it. The only thing, like basically when it becomes collaborative, like none of this stuff is true anymore. It's going to be a huge coding effort. How you're going to deploy it? Well, I'm sure Netlify. Oops, Paul. The share my way. It's all good.
Paul, you stopped the share screen.
He's fixing it. Anyway, the point is, all of these things are suddenly like unthinkably difficult. And, clearly we want to make a version of this with all of the green check marks. And so moving to the next slide, we kind of argue that it would be 8. So, I mean, we argue that CRDTs are the way to do this. And, there was already a talk on CRDTs today. We know that there are these variants of CRDTs that are based on semi-lattices. It's got these really nice algebraic properties. I'm not going to go into all kinds of details about how CRDTs work. I'm going to give you kind of like an ESP and the highlights of these things. But the way that I would like you, and the way that Matthew and a lot of other people would like you to think about these things, is that they look like ordinary data structures, like just regular maps and sets and things, except they're collaborative. So like they're, they can have concurrent users. And to kind of comment on how they work, the idea here is just that, so there's this silly illustration here, but the idea is that, so this is, these are individual users, and this is like imagining an example of a CRDT that keeps track of text. And here, what you have is a user inserting a character into their local copy, and then, the updates being propagated to the other users, and, the users should ultimately see the same state. So what's really important about these things, like from a usability perspective, is that, people update their own copies, and then because it's just their own copy sitting in their browser, they obviously immediately see the updates. There's no delay of any kind. And then, under the hood, the CRDT kind of gossips around the updates to the other replicas. And then once those users receive those replicas, those updates, they get incorporated, and then they see the change, which, is a nice way of working in text editors, of course. So that's like how you can think about them generally working. And, the main catch that, that exists basically with these things is that you can't just use them willy-nilly. Like, you can't be like, okay, well, this is going to be all distributed data structures now, I'm just going to use CRDTs. That does not make sense when there is some kind of shared state that needs to be, like, everybody needs to see the same thing. So, like, the best example of that is a bank account. It would be bad if, like, we were concurrently making edits to a bank account and, like, we somehow, I don't know, screwed something up, right? So that's a case where you would want strong consistency. So, the point here is that we can use these in a lot of applications involving user interfaces, particularly because in those cases we can often afford a more relaxed consistency model. So I just want to briefly mention the different kinds of CRDTs that exist. We're going to zoom in on one type. We're going to zoom in on the so-called op-based type CRDTs. But basically the idea is, like, we have a state-based type, we have an op-based type, and we have a delta state-based type. The state-based type, the way that you can think about it is that it, you have a data structure, and what is actually sent over the wire is the full state of, like, when there is an update. You update yourself locally, and then you send your updated state to another replica, like the whole thing, and then there's a merge function that merges this in. Op-based, which is the kind that we're going to talk about today, is just about updating and broadcasting, you update locally and then you broadcast the actual operation, like the function, or not the function, but like the actual operation that you want all the other replicas to apply. And then the last one is kind of a newer one. The way that you need to think about these is that there are new kind of state-based CRDTs, and the way that they are described, I like the way that they are described is it's very complex sounding, but it's actually very simple in the end. So you have a delta mutator that's defined to return a delta state, which is in the same join semilattice, which basically is you have a function that returns the delta of how your state has changed. That's basically what it means. And then, you send that around. So it's something tiny that you end up sending around rather than the entire state of your whole data structure. So these are the three kinds of CRDTs. It's worth knowing that they exist. We focus on the op-based kind, just because this is the sort of formal basis of our stuff, assumes that operations are flowing around. Just to say a few more words about, like, what do Matthew and I actually add to any of this. So the main issue is that CRDTs have limitations which make them less easy to use generically than we'd like them to. You can't just, so we're like, hey guys, use these as like a data structure, just willy-nilly however you want. And the problem is that CRDTs, the way that they are designed, they don't compose. And the easiest way to kind of give you guys the gist of what that means is that you can have different CRDTs operations being combined somehow, but the way that they get combined might not be actually semantically correct. And that's, when you use kind of two CRDTs together in some way. So, the point here is like the takeaway is just that the way that they're currently designed, you can't use them willy-nilly like regular data structure, like I was kind of advocating that you should be able to do. And so we have this project called Collabs. There's a paper that is under review right now, which is getting beaten up. So maybe it won't get accepted. Maybe we'll just have to publish it as a draft for now. But something will come out soon, which will describe them. But it's based on this paper that we published at ICFP 2020, where it's all about like how being able to do composition with CRDTs. And so Collabs are basically like a library that kind of ties a whole bunch of things together. And the idea is that Collabs guarantee that you'll correctly compose operations as long as you use data structures that live within this framework. And you can define data structures that live within this framework. And there's actually a bunch of composition techniques that we use. So the semi-direct product, which is the thing in this ICFP paper, it's mathy, so you don't kill yourself with it. But the point is that it's a nice like arbitration order kind of. Paul did a wonderful job of like tweeting about it and tweeting an example where he did it in Unison. So like maybe look at that before looking at the actual paper. And then having collections of CRDTs, or this notion of like a CRDT, like a composite object, very object-oriented way of doing it, but like, using some of the techniques that Matthew has talked about in some of the work that we have. So it doesn't, the point is not to like give you all the details of Collabs. The point is actually just to give you some insight. And the insight that I would like you to walk away with about what these Collabs things are is just a collection of techniques that enable CRDT composition, but as an API design, like as a library. So we don't like implement any crazy compiler, or type system tricks to like check your CRDTs. We design a library where you're supposed to just compose things. And, as long as you don't pass a bunch of side effecting, crazy, scary things into them, you're guaranteed that these things will compose. Then the whole point is to be able to use CRDTs like regular data structures, finally, and I can model my data like in, sorry, I'm going to talk object-oriented land, but make a class with some other nested classes, model your data how you would model your data and without violating eventual consistency. So this is just kind of like a picture of how you can think about these things. So you have a front end, and then your data structures you would be using are Collabs. You can have sort of any network in between. So you need like a broadcast, like messaging, like a group chat kind of protocol in the middle, which sends updates to everybody. But then that can live on top of any sort of network. And Matthew has actually implemented a lot of these things on this decentralized network called Matrix. So that shows you that it's like purely peer-to-peer. There's no centralized server at all. And the way, so pardon my, I guess this is technically Scala, but it's basically the TypeScript interface. So if we have like some original version of these ingredients in the list that we just in the app example that we just saw, we have the regular types, right? Like the name of the ingredient, the amount, the units. And really the main thing is that, you extend it with some of these Collabs things. And then you have a bunch of CRDT versions of these data structures. And that's really all you have to do. Then you use the same like update, increment, etc. operations that you would for a regular data structure is kind of like the takeaway. Okay, so you might be like, okay, well, this is very, very object oriented, right? So what the hell am I doing? What's Heather going on about? This is Unison for all. So what do these things look like in Unison? This is where Paul comes in. He's like, look, I'm going to Unison foo this. And and here we go. So please.
Yeah. Awesome. So, I mean, I thought that, the research that Heather and her students have done is super cool, and I was excited to try porting it to Unison. Sort of one challenge is kind of maybe, as Heather said, the way that they're expressed, the collaborative data structures work. It's done as this kind of object-oriented style library where kind of this mutable state is kind of hidden in the implementation of these classes.
Extremely object-oriented, which is perfect for TypeScript, but maybe not Unison.
Yeah,
Maybe.
So it was like a fun challenge to figure out how to express that sort of thing nicely.
Un-OOify.
Yeah. But yeah, so I wanted to show just kind of what we've sketched out so far. So the main entry point for this library is this function CRDTs.run. And you give it a computation that uses remote and this ability CRDTs, which I'll say more about in a bit. And it's going to sort of compile away the CRDTs stuff into remote stuff. So at the end of the day, when you're doing CRDT stuff, it's going to have to be sending messages and broadcasting the ops to other participants in the computation. And so, but we want to express that with a nice high-level interface, but then just have it compiled down to remote. And so that's kind of what this handler does. And then here's like an example usage of it. And this is meant to look like super straightforward. So we're in one of the CRDTs run block, and we are declaring a concurrent map, favorite fruits, and then we just are forking a computation at two different nodes, which is going to update the favorite fruits map. And so this is like a shared mutable map that can be referenced at multiple locations in the distributed computation.
And then just use like a data structure, like
you just
updating your keys. Like there's no fancy distributed nonsense happening in those calls. I mean, that you can see.
Yeah. So it's meant to just feel very straightforward. And then when you in this example here, like we've bumped Kiwi up by 1 at these two different locations. So eventually everyone is going to see a value of 2 for Kiwi. But it's eventually consistent, so it may take a little bit of time to converge to that value. So just a little bit more about the API is there's a few different data types. There's concurrent maps, there's accumulators, there's registers, there's concurrent sequences, and then there's a nice framework for how you can build your own new collaborative data structures within this framework. And also, of course, you can nest these things, so you can have a collaborative map where the values are a collaborative sequence, and you can kind of nest things and build up more complicated data types in that way.
Yeah, I think this is that point. Like you can model your data how you want to model your data. Like you don't have to try to like deconstruct it and put it in like a map. You just model it how you want to.
Yeah. Okay. So I was going to show, okay, what if you do want to define your own new data type in this framework? So there's kind of like a couple key ideas. So one is we want to separate the logic of the op-based CRDT from the kind of messaging and networking stuff that is going to have to happen behind the scenes. So when you're defining a CRDT, which is sort of the core logic of one of these data types, you do it with this simple type or this interface CRDT, and there's a model, and then there's some operation type, and then there's a function for how do you apply the operation to the model to produce a new model. And a really simple example of creating a CRDT is, the model is a natural number, 0, and the apply function is just max. So just taking the max of the natural numbers. So that's sort of the simplest version. In the library that we started developing, we kind of generalized it a little bit. It's usually a good idea to allow effects on these function arrows. Because what that means is like, oh, okay, now you can actually have CRDTs that are like a distributed key value store. So it doesn't necessarily need to be something that just fits in memory on one machine. You could have an operation that's like, oh, insert this value into the key value store, but the key value store could be a distributed thing. And this is really just straightforward to do, and it doesn't really affect the ergonomics of a library. So it's often good to generalize over effects like this. Okay, so the CRDT's ability has these three operations. So one is we can create I call it a CRDT reference. So you give it some CRDT logic, and then it gives you back a CRDT ref, which is sort of typed according to that CRDT. And then you can read one of those refs, and you can apply an operation to a CRDT ref. And this NAT here is just used for thread safety of updates at a single location. But I'm not going to talk too much about that now. But okay, so I was thinking we could actually, so that's literally the entirety of the interface in terms of the primitives. I was thinking we could try just walking through a little bit of like how we would implement CMAP. So CMAP is not like built in. It was CMAP was built using
these primitives.
Yeah, these primitives that I just showed.
But you need to remember the ability as we go, because it's interesting later.
Yes. Okay, so going back to our example CMAP, where we were using CMAP earlier. So we have some way of constructing an empty CMAP. We have some way of doing update. We have some way of doing lookup. And in this case, our CMAP, it's the values are accumulator, or a counter. I'm not going to go. This is also another data type that's implemented with the library. I won't go through it in detail, but this is sort of what the interface is. You can.
It's a CRDT though, and
this is also a CRDT, sort of a simpler, even simpler CRDT.
It's like, yeah.
Okay, so here, maybe Heather, do you want to try to explain like why? Yeah.
Okay, explain why vector clocks. So actually, the CRDT talk earlier went into a bunch of details and had a nice like illustration of vector clocks. So if you saw that, like, I'm not going to repeat all the details over vector clock or anything. But the point is that there exists vector clocks, within this implementation, because ultimately, if you're going to be implementing some kind of custom collaborative data structure of some sort, you need to be able to compare when different updates happened, so then you can know when to, like, what to do with them. So vector clocks help us know that. So the idea really is to determine when two events are concurrent, or like if we have some causal order of events or concurrent. And then if there's concurrent, then you have to do something, right? You have to resolve this provide some update that would be deterministic across other devices. So that's the vector clock helps you decide when that happens, is sort of the reason why it's here. And it lives within it's not just to scare you with funny distributed system sounding words. It's, the point here is that this stuff actually lives underneath the covers, and you should not have to deal with it, but it's there.
Yeah, and so specifically with CMAP, it comes up because if like Alice does a delete of a key of the map and Bob at the same time does a create or an insert of a key, then there's like the question of like who wins. First of all, like how do you detect that those two operations happened concurrently? And then
once you know that they happen concurrently, you have to do something. So like the vector clock solves the first problem. The second problem, though, is actually something that you have to decide yourself. And that's a little daunting, I think, for a lot of people. So this is why there's like umpteen bazillion kinds of CRDTs. So like there will be a bunch of different variants of CRDT maps, not only for performance reasons, because some are faster than others or more memory efficient than others, but because they actually have differing semantics. So in this case, what we're trying to show is or actually there's no logic here. There's just interfaces. But the point, you might want to have the results of this concurrent thing be, oh no, like deletes always win, right? And instead of, adds win, right? So like if there's an add and delete at the same time, which one should be the one that wins? And so you choose those semantics as the person selecting the data structure.
Yeah. But basically when in creating CMAP, all we're really doing is we're mapping a CRDT ref, we're wrapping a CRDT ref, and then just kind of writing some convenience functions. So I'm not going to go through this code in detail, but this is the literal implementation of CMAP.empty. You can see it's doing some stuff, checking these vector clocks to see if there's been a concurrent delete and create. And in this case, it's doing delete wins, but you could easily implement create wins. And here's just implementation of lookup. Also just super straightforward. It's basically just reading from the CRDT ref and then, doing a map lookup and returning the result. And so the actual handler of this, so the thing that's actually running these CRDTs computations and sort of interpreting all that stuff away into remote, that is doing a lot of heavy lifting so that the client code, the user's code, stays beautiful. I'm not going to go through like what all these things, but yeah, there's fairly intricate stuff that the CRDT's interpreter has to do to compile that stuff away into remote.
Maintaining all these maps of like identifiers for CRDTs, that's something that you do not want to do, I promise. And this is like the magic of abilities and being able to put all that stuff in the handler so that you don't have to see it.
Cool. Yeah. So Heather, do you want to just wrap up?
Yeah. So so I guess there's the one thing that I was just ranting about again and again, which is the fact that I think abilities make distributed APIs really nice. Obviously a lot of the time we want to hide ugly implementation details, but, and there are different ways to do this in different paradigms, but I find this to be a really nice way to kind of deal with those messy details and keep them away from the user. The other point here is also that like some of the stuff that we showed, these are sketches. It's not like an implementation that you should like go and try to download and use or something. We were just trying to figure out how these things would look in Unison. So like caveat, this was an exercise more than it was like, hey guys, here's a wonderful library for you to use. And sort of like the last point, is that I think, clearly more experiments are required, but I think it was, really nice to see that these things could be represented within Unison's distributed APIs and sort of just general language features. Like we did not need to like add a new something for distribution in order to realize these things. So, more evidence is needed, but I do think it's, it kind of shows that Unison and the distributed package is a nice foundation to build these kinds of applications on.